So anyways, I'm going to be on page 5 and 6, and I just want to talk about what a derivative is. And based on stuff we just did the past few days, derivative isn't new. It is, so I just haven't called it a derivative yet. The derivative is the function we found in that last section or two that represents the slope at any point. It was the function like when we leave it just in terms of a. So if they don't give you, they could give you the x-coordinate, but it's when you don't plug in like 1 for a or any number for a. It's that function you give that has a in it. So I said at the top, the limit we found in that last section, the slope of a curve at a point, is called the derivative. So conceptually, this is what it is. It's a function that represents the slope at any point. Instantaneous rate of change, IRI. So remember on like x squared, and we've got this. So what that said is, all right, that's a function that represents the slope at any point. I could plug in x equals 1 for a, and that's the slope at x equals 1 for x squared. Right, here's 1. Plug in 1, and that would give me whatever that slope is. 2 times 1 equals 2. So that's what the derivative is. I wrote it again for you there, right here. If you'd rather, this is how it's normally written with the x. If you'd like to change this to a, you can. It's just normally written with the x. And something else I want to say, we don't do a lot of this, but remember how there's limits, and there's one-sided limits. So it was like, in order for the limit to exist, the left-hand limit and the right-hand limit had to be the same. There could be a hole there, but left and right-hand limit have to be the same. Same for a derivative to exist. So the derivative represents slope. So this time, a common example is absolute value x. So if you choose like this point on absolute value x, the slope on the right side is 1, and the slope on the left side is also 1 of that point. So that works out. But right here at 0, the slope on the right side is a positive 1, and the slope on the left side is a negative 1. So in order for the derivative to exist, the slope to exist, the right and left hand slopes have to be the same. Okay. I don't think it's saying, oh, that was my example. Okay, good. So not a whole lot new right there. It's just I'm calling it a derivative, not that much. Okay, now here's some new notation. You have a function f of x, or f of a, or f of z, whatever you want to call it. Here's how we're going to write the derivative. You put this apostrophe there. Must have it on the next page. You put that apostrophe there. Here it is. That represents, we call it prime. So I'm going to be saying f prime of x. Looks kind of like an apostrophe kind of thing. It's actually just it's straight. It's not actually curved like that. So on the one I'm looking at here, I didn't do a great job. It really is just a straight little line. That's right, f prime of x, or maybe if the function's y. So it might be y prime. It could be z, and then z prime. So that's one way to write it. Now here's another way that we're going to write it. So say the function was y equals 3x. Well, this is another way to write the derivative. This you say is dy dx, which represents the slope. It's actually not a fraction. Okay, like it's not. It looks like a fraction, but it's just the way we write it. And they honestly should have just put it like this, but then it kind of looks a little misleading. It's not actually like a fraction that you can solve. It's just the way they write it, just a bar. So here's what this means. This way is actually slightly better because it tells you what variable you're taking the derivative in respect to. So what I mean by that is right here it says dy dx, the derivative of y with respect to the x variable. That's what this means. Derivative of y. This tells you what variable it's in respect to. So what I'm saying is like, well, what if the function was f of z equals 3z? Well, then you would need to do df dz, the derivative of the f function with respect to the z variable. And so it's all about variables. I kind of said there was an f and an x one. There's one other way those are the like 95% of the time you'll see those two. There's one other way you'll see it written. They'll just list a capital D and then put the variable subscript. So the last example I have there is d sub x. That means the derivative, find the derivative with respect to the x variable for this function. So they could say like dz with respect to this function. Derivative of the z derivative with respect to the z variable for this function. Okay. Had a little technical notation there. Any thoughts right now so far about derivative or the ways we're going to write it? By the way, you'll see it so much that you'll just get used to the way we write things.
What do you mean when you say with respect?
With respect to just what the variable is in the equation. So like here, this one, the variable in our function is z. But I could have, so right now we want to find the derivative of f with respect to the z variable. That just means the variable z. But what if I changed it to x? Well, then it would be the derivative of f with respect to the x variable. Just whatever variable is in the function. Thanks. Any other thoughts, questions? So I'd like to try, now this is the time where I'd like to do an example, and then I'm going to do the same example with the alternate form. We haven't done the alternate one, I don't think yet. So I'm going to do one, and then from now on you can actually choose whichever one you like. So we're going to use the normal form right here to find the derivative of that function, radical z. Here, I should write it like this. So I'm going to write it. We're finding f prime of, let's see. So we're going to find the derivative. And I'm just going to use the limit here. That's what the derivative is. I'll go ahead and use a, since we're kind of used to that. Again, this is a dummy variable. You can use x or whatever you want here. I just normally been using a. Okay, so let me just write it out. Okay, so normal formula. Again, this is just another example. We did one like this previously. You don't plug in anything for a. You just leave it as a. Okay, so it's radical z. So right here I'm plugging in a plus h for z. So it becomes radical a plus h. Oh, I forgot to write limit. Minus, and then this one is f of a, so I just plug in a for z, and then over h. And now it's a limit question, and we think about how to solve it. It's similar, there was one in the practice that we did yesterday, the day before, that looked like this. It's conjugate. It's conjugate one. I think it was 3b. Yeah, 3b. Because there's no FOIL, there's no factor. But there's square roots, and that can lead us as a conjugate. Okay, so the conjugate is in the numerator, radical a plus h, and then we'll change it to a plus radical a. And then we do that to numerator and denominator. But in a second, I only will distribute the numerator. So I'm already writing this. And the denominator, the part that was originally no square roots even in it, you don't need to distribute the bottom. Okay, but in the numerator we will. We need a FOIL. It looks like a lot, but again, when you do these, they quickly cancel things out. So on this one, the f is a plus h. Radical a plus h times radical a plus h is radical a plus h squared, and the square roots square and the square root undo itself. So it's just a plus, that's h. As always, the outside and inside terms in the conjugate cancel. It would be positive radical a plus h minus radical a plus h. Cancel. And then last is minus radical a times radical a is radical a squared, which is a. And as you can see, the a's cancel. And once the a's cancel, the only thing that's left up top is the h. Right, this is all gone. That's an h. H over h, now I can cancel this. And so all that's left in the numerator is a 1. Sometimes students forget that 1. And since I canceled the h, now I can plug in 0. So it's radical a plus 0 plus radical a. So here's the final derivative, 1 over, well, this is just radical a, right? A plus 0 is a. So radical a plus radical a is 2 radical a. That is, again, what it represents. A function that represents an instantaneous rate of change, this tangent slope, at any point. So whatever x coordinate you want to find the slope at, you plug it in for a. Okay. I'm actually going to flip, we're going to flip it over in a second to see if there's any questions. We're going to do the same one, but same question, but in the other form. So what are your thoughts on the first form, though? What? The f prime of z? Yeah. You know what I'm saying? That's just the way we write it. So I could have written it all along. I just kept writing equals, though. So f prime of z, this just means the derivative of that function. And it's this, 1 over 2 radical a. That's the slope at any point. That kind of answer. So flip it over, and you said we're going to do the same question, but here's the other form. I said an alternate definition of derivative. It's just a different way to write the slope formula. I say it's not used as often, but I really don't care which one you use, and we've done the other one a lot. I just want to show you this one. Sometimes it can be easier, actually. Sometimes it's harder. So the other one is just more sure. Like the other one will basically always work well. This one works every time, but sometimes it's a little harder to see, and so that's why I don't use it as much. So this is the more traditional, like y2 minus y1, x2 minus x1 formula. So same function. Let me just show you how we could use this one. Limit as h, oh no, I'm sorry. Yeah, this one, here's the difference. It's not h approaches 0, it's x approaches a. F of x minus f of a over x minus a. Alright, so this one we'll do is we'll plug those in, and then once you cancel things, you plug in a. Like it used to be h approaches 0, you plug in 0. X approaches a, you plug in a. Alright, some of the substitution on this is actually slightly easier. This is just f of x, so you plug in x here. You plug in x for 0. So it's radical x. Minus f of a is you plug in a. So it's radical a. Plug in a over Over x minus a. So the initial substitution can actually be a little easier on this one. It again becomes a limit problem, and there's no FOIL or factor, but there's square roots, and it's again a conjugate one. So let's do that. Radical, I do the top one, radical x plus radical a. So I multiply that numerator and denominator, but I'm only going to FOIL again the numerator. So I'm just writing it. I'm going to leave the denominator. I do not FOIL that. Seriously, I hit it like 3 times, didn't I?
You corrected it.
I really don't know what happens sometimes. So then I got to FOIL the numerator. F, radical x times radical x is x. This would be radical x squared. As always, the outside and insides cancel. It would be radical xa. And then minus, this one will be radical xa. And then last, minus radical a times radical a is a. It would be radical a squared, which is a. And as you can see, again, you don't FOIL the bottom, and so it'll cancel. And there will still be a 1 left up top. And finally, you plug, so this one, we canceled, now you plug in a, in for x. So normally it's h, you plug in 0, now it's x, you plug in a. So there's a 1. In place of x, I put a, I bring down that radical a, and now it's just like the last one. This is radical a plus radical a is 2 radical a. And we got the same thing. So again, moving forward, you are allowed to use that one. You're allowed to use the normal one we've done. I don't really care. Again, what I said is the first one, it just seems to work a little more surely every time for our purposes. So. Okay, I'd like to finish up with one other thing about derivative against slope graphically. So anything on what derivative is, the alternate form? Okay, yeah, that's perfect. So last thing I want to do to talk about today is graphically, what's the relationship between f, the original function, and f prime? F prime is the derivative, or it's a slope function. We just call it the slope function. Let's see. So here's an example this is not on your page, but just an example you can see. This is the original function. Yeah, this is what I call it y, and this one's y prime, the derivative function, the slope function. So what you can do is you can figure out some slopes, okay? I'll start here, like at the top here. If I do the instantaneous rate of change right at the top there, the slope would be horizontal, and a horizontal slope is 0. So what you do is on the derivative graph, at 2, the derivative y values must be 0. So you come over at 2, and that's why it's crossing at 0 here. This plots the slopes. That's what the derivative y prime, it just plots all your slopes. So now they gave us some, you're not always going to be able to know some of the other ones, but like, they said, all right here, the slope is, somehow they knew the slope is 1. So what's this, like 1.2 or something? You plot the y coordinate as a slope of 1. And you can see, others. Here was another one we definitely knew. At 6, the slope is horizontal, so it's 0. Basically, slope of your original becomes your y coordinates over there. And I think I say that. I added it on your page here. Think of the derivative in graphically slope. So for a normal xy point, the derivative, f prime, put on yours, it becomes x down. So you take the normal x coordinate, but you plot the slope. Like here, the x coordinate was 2, and I plotted the slope as my y value of 0. That's what I mean, x and then your slope. And one other point about that is I say for polynomials, this is important, the derivative takes the degree of a function down 1. Takes the degree down 1. So let's use that on this one here. This function is f. Okay, they've given, it says here, they've given f. Get a general graph of f prime. So they want us this to be f prime. All right, so using the last thing I said there, this is a polynomial, right? It looks x cubed like, roughly x cubed. It's going to, go up and down a little bit here. So over here, the derivative takes the degree down 1. So over here, it must be something like x squared. All right, if you have a polynomial, this is something we know. So I'm going to draw a general graph of x squared over here. Now, I can get a little bit more accurate because right here, I know these slopes will be 0. Right, we're at a max, a little bit of a maximum and minimum here. So let's do this. At x equals -2, the slope is certainly 0. So over here at x equals -2, again, I'm plotting x down. So at -2, I can plot my slope, -2, and then 0. And the same thing over here. This is just past 0, so maybe like 0.5 or 0.2 or something. The slope is also going to be 0, so I can plot about 0.2, or 0.2-ish. 0. Other than that, now I know some general slopes. For example, all the slopes here are positive, right? Would you agree it's going up? So all the slopes here would be positive. So over here, let me go and draw it. It's got to look like x squared going through these. Something like that. You see how to the left of -2, everything was positive. If the slopes were positive, so over there the y values are positive. And then what happens is in between here, the slopes are all negative. So that's why here to here it was below the x-axis. And then again over here, all the slopes are positive, and that correlates with the y values there. So a couple good things, and for polynomials, the derivative will take the degree down 1. Okay, sounds good. Yeah, we better stop there. I might have time to finish. Yeah, I'll start tomorrow. Just finish that last one really quickly. Any things on that first example though? Okay, so to finish this one up at the bottom here, this time this is the function f prime, and they want the graph of f. And so first of all, they give us f of 0 is 0. That point is here. We know that. Now, this is over here. These are slopes, right? This is a slope function, the derivative. So it's actually pretty simple. I'm just going to run through it really quickly. To the right of 1, actually I need to start, we're on the left of 1. Let me start here. To the left of 1, this is x equals 1. This is saying the slope is -1. So over here, on the right graph, I need to do a slope of -1. Like that. Right? Down 1, right 1, or up 1, left 1. And I do it all the way to 1, because that's where I know that the slope is ending there. And then to the right of 1, the slope is, I was going to say 1. The slope is 2. And so to the right of 1 over here, I need to go up 2, right 1, up 2, right 1 to get a slope of 2. And that's it.